Hello everyone. In this section, I will show you how to use definite integral and also improper integral of type 1 to deal with questions involving a flow of money or continuous income funds. In the first definition, the situation is the following. So this is you. So suppose this little stick person is you. And suppose you are receiving a stream of income. And suppose that stream of income is modeled by CT, C4, cash. So this stream of income goes to you. So this is some cash that you receive continuously. It goes to you. And you're receiving that amount of cash for T years. And you have access to a bank account. And you're putting that cash in that bank account. And that bank account has for you an interest rate. So interest rate of R. So R, of course, for interest rate. Then, so if you are receiving this flow of income for T years and you're putting this in a bank with an interest rate of R, this is how much money you will have. So this is how much money. So you're not just receiving this flow of income, but this is how much money you will have. So this future value that you're going to get is the definite integral from 0 to t of ct times e to the power of r, open bracket, big T minus t dt. So in these questions, big T is always given. It's a fixed number. Ct, the function that models how much cash you're receiving, is also going to be given. So this question is just a question of plugging the right information in the right spot, and then, of course, computing an integral. And typically, as soon as Ct is not a constant function, you will need to use integration by parts to compute these final answers. So here's an example. So let Ct be equal to 2t plus 14. Suppose Ct here is in millions of dollars per year. Let's compute the value of the annuity after the first 5 years if the annual interest rate is 8%. And suppose that is compounded continuously. So again here, just read your question, extract the information. In this case, we're doing this for 5 years. So big T is equal to 5. And because the interest rate is 8%, the R value is 0.08. So the definite integral that you need to set up is the integral from 0 to 5 of Ct, being explicitly given here to be 2t plus 14, times e to the power of the interest rate, so 0.08 times 5 minus t, the 5 being the big T here, dt. And if you want, maybe you want to multiply the 0.08 inside to simplify this a little bit. It's really up to you. So that's just setting up the definite integral that will compute how much money you will have in your bank account after the first 5 years. Then the question is basically over. The first step, you forget about the bounds. You write your question as an indefinite integral. If you do the indefinite integral of 2t plus 14 times e to the power of 0.08 times 5 minus t dt, you can get, using in this case by part, I have the details if needed for you in this question, but you can get that the family of antiderivative is minus e to the power of 0.4 minus 0.08t times 25t plus 487.5 plus c. And then by just replacing c by 0, you get an example of a primitive, and I've called that primitive big F of t. Then you go back to your definite integral question. You want to do this between 0 and 5. Pas de problème. By the first fundamental theorem of calculus, I'm going to compute big F at 5 minus big F at 0. And you should double check, just by evaluation, that this simplifies to 114.7645 millions of dollars. All right, that's it for that example. So next definition. Suppose again we're dealing with a continuous income function, CT in dollars per year at time t in years. So suppose we want to compute first how much cash is earned over t years if you're receiving this continuous income function. Well, this is going to be given by the following integral. So the integral from 0 to big T of CT dt is, poof, how much cash is earned over t years. So if you're receiving this stream of income for t years, this is what you get. So be careful. This question is slightly different from the previous one where we were receiving CT, but we were putting that money in a bank account. So this is more from the point of view of the one who gives money. If you want to compute how much money you're giving away over t years, this is what you're going to be computing. Now, if you want to give away that money, but you have access to a bank account where the interest rate is given by R, and you want to know how much money I need right now in my bank account to give this continuous income to whoever, then the integral that will compute how much money you need now to set up this continuous income function will be given by the integral from 0 to t of ct e to the power of minus r t dt. And this is going to compute for you how much cash is needed now. So this is going to compute, sorry, little problem. Boom, this is going to compute how much money is needed now in your bank account to in order to give CT for big T years. So that integral computes how much money you need right now. And suppose for some reason you want to know how much money you need now to give away the stream of income forever. So basically you want to set up a perpetuity. So if you want to compute how much money you need right now in your bank account, suppose the bank account again gives you access to an interest rate of R. So the present value is going to be given by the integral from 0 to infinity. So that's an improper integral of ct e to the minus rt dt. So that improper integral of type 1 is going to compute for you how much money is needed now to give away CT forever. Okay, that's a perpetuity setup for us. Again, let's just do an example to assimilate these three integrals. All right, let's compute the total income earned over a 4-year contract where the continuous income is given by CT equal to 90,000 plus 11,000 T, and then compute the present value of the fund in order to give out. Okay, basically that's CT. If you have access to a bank account where the interest rate is 1%. So first, the total income is the integral of CT from 0 to 4. Again, when you're computing a different integral, the first step is you just forget about the bounds. Let's just compute a family of antiderivative for 90,000 plus 11,000 T. So you're going to get 90,000 T plus 5,500 T squared plus C. So if you want one primitive, let's call it, let's say big G of T. Let's use 90,000 T plus 5,500 T squared. Now, if you want the total income from 0 to 4 of that CT, by the first fundamental term of calculus, it's going to be big G at 4 minus big G at 0. And once you compute your value for big G at 4 and big G at 0, you're going to get $448,000. So this is how much money you're going to earn if you're receiving that flow of income for 4 years. Now, if you want to compute the present value, so how much money you need right now in order to give as much money for the contract over 4 years, this is what you need to compute. You need to compute the integral between 0 and 4 of CT e to the power of minus 0.01 t. Again, initially you don't care about the bounds, so you can view this as an indefinite integral question. So let's compute the integral from 90,000 plus 11,000t e to the power of minus 0.01t dt. This will be equal, you will need by parts here, this is a good exercise, to minus e to the power of minus 0.1t times, open bracket, 1,100,000 t plus 119 million, close bracket, plus c. So if you want one primitive, you can choose minus e to the minus 0.01t times 1,100,000 t plus 19 million. So if you want the present value, now you need to integrate between 0 and 4. So by using the first fundamental theorem of calculus, big F at 4 minus big F at 0, you can double check that. This will give you $438,583.20. So you don't need as much money, so you can have a little bit less, because as you're giving away money, you're still making money for the money that you have in your bank account. So that's the present value that you need if you want to give away that total income computed in the first with the first definite integral. So for the last example, let's compute the present value of the perpetuity that pays CT equal to 90,000 plus 11,000 T using the same bank account with the 1% interest rate. So this is, of course, a sequel of the previous example. So same stream of income that we want to give away, but we want to give it away forever. Okay, so the present value when you're doing this forever, so we're talking about the integral between 0 to infinity now, because we're doing this forever, of CT, 90,000 plus 11,000 T e to the minus 0.01 T dt. So this is an improper integral type 1. So we want to get rid of the improper bound, which is infinity here. So we're going to replace infinity by, let's say, b. Cannot use t here because t is already time here. So I'm going to use b as the upper bound. So same integral. So 90,000 plus 11,000 t e to the minus 0.01 t dt. But now we're going to push that b to infinity. So that's my improper bound. The infinity symbol was replaced by b, and now we're pushing b to infinity. Again, in these questions, it's absolutely crucial that you set up your improper integral correctly. It's the most important part of the question. Okay, so after that, things are very straightforward. So let's go over the steps quickly. So we can use the same primitive as before. So for big F, I'm going to use again minus e to the minus 0.01 t times, open bracket, 1,100,000 t plus 119 million. So that's for the primitive that I'm going to use in my question. So the second step is to compute the definite integral between 0 and b of 90,000 plus 11,000 t times e to the power of minus 0.1 t dt. So by the first fundamental theorem of calculus, it's just f at the upper bound b minus f at the lower bound 0. So if you evaluate at b minus at 0, you can simplify and get 119 million minus e to the minus 0.01 b times, open bracket, 1,100,000 b plus 119 million. Now that I have my definite integral computed from 0 to b, we want to study what happens when b gets larger and larger. So we want to compute our limit as b goes to infinity. So our improper integral from 0 to infinity will be the limit as b goes to infinity of the definite integral from 0 to b. So this will be the same as computing the limit of the formula that we freshly obtained earlier as b goes to infinity of 119 million minus e to the power minus 0.01b times open bracket 1,100,000 b plus 119 million. So when you plug b by infinity, the first term is a constant, so you can take it out of the limit. But sadly, e to the power of minus infinity will be 0. And then that linear function, when you replace b by infinity, you're going to get infinity. So when you have 0 times infinity, that's bad. But no worry, the exponential function, we can move it around. We can bring it down at the denominator as e to the power of 0.01 b. And now if you replace b by infinity, you have infinity over infinity. So you can use Hospital rule. If you differentiate above, you're going to get 1,100,000. That's it. Over, for the denominator, you need a small chain rule, e to 0.01b. If you compute its derivative, you're going to get 0.01 times e to the power of 0.01b. And now when you plug b by infinity again, you're going to get a number over infinity. So this whole fraction will go to 0. All that to say that the whole thing will go to 119 million dollars. So in other words, if you have right now in your bank account $119 million, you can pay a flow of income CT forever. Okay, so all right. So for that section of how to use definite integrals and type 1 improper integrals to compute various things, that's it. That's all. Bye-bye.